In this video, we're going to take a look at what is truly the foundation of most statistical studies, what is truly the foundation of inferential statistics, all based on probability that we have seen before, this thing called the normal distribution. And our essential question for today is simply, what is the normal distribution? And so to start answering this question, the normal distribution is a probability density function. It's continuous. And the formula for the normal distribution, the uniform distribution, you remember we saw in our previous videos, was 1 over b minus a. The normal distribution is a little more involved. It's 1 over the standard deviation times the square root of 2 pi times e to the negative 1/2 times x minus mu divided by sigma squared. Now the beautiful thing is we don't have to actually memorize that formula. I like to look at it though so we can understand the complexity of something that is so simple to work with and understand and use. Now notationally, if the random variable x is normally distributed, we will use n, and then the variables inside our n are going to be mu, the mean, comma, sigma, the standard deviation. And again, we will use a table. And in class yesterday, you should have gotten this table given to you. This is the normal distribution table. We'll talk more about how to use it later. But as you saw in the little graphic, the normal distribution starts shallow and comes up in a bell curve shape and then levels off. And the idea is the mean is right in the middle. Most values are going to be close to the mean, and the farther you get from the mean, fewer values are going to be out there farther from the mean. It's completely symmetrical, which is going to be nice, so we're just as likely to be 2 standard deviations above the mean as we are to be 2 standard deviations below the mean. To help us actually use a table, though, first we need to understand how to use the standard normal distribution. And the idea here is we can take any normal distribution and standardize it into a z random variable. And the way we calculate the z random variable is we take our x from the original distribution, subtract the mean, and divide by the standard deviation. It comes from the formula we've seen before where x is equal to z, the number of standard deviations, times the standard deviation plus the mean. Notice if you solve that formula for z, you end up with the formula that we're talking about today. X minus mu divided by sigma. But before we get really into that, let's really tear apart the standard normal distribution and make sure we understand it and how to use it. So now z is our random variable on a normal distribution. With z, the mean is always 0, and the standard deviation on the standard normal is always going to be 1. And the nice part there is that's where we get the table that you've seen before. This table actually is for the standard normal distribution, which means here the mean is 0. You'll notice in the little picture the middle has a mean of 0, and the standard deviation there is 1. And if everything gets standardized to this guy, the table gives the values for all the different z values on either side. We'll talk more about that in a minute. So what we want to be good at, what we want to be comfortable with, is how to find area with the table. And you remember with continuous distribution functions and PDFs, probability density functions, area is the same as probability. So we're really finding probabilities with the table. What's important to note, though, is on the standard normal, we look up a value maybe of 2 in the table. The table is going to give us the area between that number and the mean. So table gives this, I'm going to say. Which means we need to know how to take that piece of information and interpret it for any piece of area on the left side, on the right side, in the middle. So a couple key things to remember to find area is each half, and because the halves are symmetrical, each half has 0.5 area in it. The other thing we're going to remember, going back to that, is that it is symmetrical. So negative 0.3 and 0.3 have same areas. In other words, visually what I mean by this, these aren't really good, but hey, here's 0.3. Negative 0.3 is over here. They're on opposite sides, but they are the same area because it's symmetrical. So we're going to use that as we solve problems like, for instance, we want to find the probability that z is less than 1.12. I will always start by drawing a picture to help me see what area I'm looking for. So the mean is 0, and 1.12 is over here. We want z to be less than that, and so we want all of this area. Fortunately, we know the right side is already 0.5. The left side is where we're going to use the table. The left side, we want the area between 0 and 1.12. So we go, the first decimal point is always on the left, 1.12. 1.12, on my table, I see the area is 0.368. And that's just using my table, 1.12 to the 0.3686. 0.3686. And so if I want the total area that comes from that, we're going to add the pieces together because I want both of them. 0.5 plus 0.3686 gives me an area of 0.8686. So the probability that a z-score is less than 1.12 or less than 1.12 standard deviations from the mean is 0.8686. Let's try another one. Let's find the probability that z is greater than 0.73. So the mean is 0, and 0.73 is over to the right. Doesn't have to be to scale, but just gives me an idea. And I want z to be greater than 0.73. But here's the catch. The table is going to give me the space between 0 and that value. So we're going to have to work a bit to get the right side, because the table is going to give us the left side. Going to the table, though, 0.73. Let's do this in blue. 0.73, and so that value is 0.2673. 2673. But we don't want that half, we want the other half. But fortunately we remember that the entire right side has an area of 0.5. And what we don't want, so we're going to subtract it out, is the white space of 0.2673. And so if we do 0.5 minus 0.2673, we get 0.2327. And so the probability that we are more than 0.73 standard deviations above the mean is 0.2327. Let's try another one. How about the probability that z is between two values, between 0.3 and 2.41? Again, we'll draw a picture. The mean is 0. So 0.3 is here, and 2.41 is further to the right. So what we want is that area in there. Now the table is going to give us two probabilities. The table can give us the probability of the white space and the probability of everything between 241 down. So let's find those two values. First, 0.3. On the table, I'll do this in green. 0.3, nothing after the 3, so we go 0.30. So that's 1179. 0.1179. That's the white space. Then when we do 241, I'll do it in green again. 2.41. 241 is 0.4920. 0.4920. But again, that's from the 241 down to the 0. We don't want the white space, which is the 1179, so we need to subtract that out. 0.4920. Subtract out the white space we don't want of 0.1179, and I'll do that on my calculator, and I come up with 0.3741. So the probability that we're between 0.3 standard deviations above the mean and 2.41 standard deviations above the mean is 37.41%. Let's try another example. These have all been positives, but z values can be negative. Negative just means to the left of 0, and we'll use the symmetry to help us with this. Let's see the probability that z is greater than negative 0.76. Again, we'll draw a picture of this bell curve. 0 in the middle, this time negative 0.76, because it's negative, is off to the right. And we want z to be greater than it. So greater means we're going up. We want all of this area. Again, we already know the right side is 0.5. The left side is just between 0 and 0.76. And because it's symmetrical, we can just look at positive 0.76 on the table. I'll do this in pink. 0.7. Actually, let's erase a bit. Got a lot of stuff on here. It's getting too crowded. Positive 0.76. 0.76. So the area there is 0.2764. 0.2764. And this time we want both areas, so we'll add them together. 0.2764 plus 0.5 is 0.7764. Let's do a couple more examples. How about the probability that the number of standard deviations from the mean is less than negative 0.213? And because it's negative, we're talking about being below the mean. Well, that's a terrible normal curve. It's supposed to be symmetrical. That doesn't look symmetrical. We'll go with it. Negative 2.13. It's negative, so we're off to the left. And we want z to be less than that value. So less than that value is going to be the tail off to the left. Remember, the table will tell us the middle, the area between 2.13 and 0. And so when we look up 2.13, 2.13, we have an area of 0.4834. So that area is 0.4834. Check that, make sure it's right. 4834, yep. But we don't want that area, we want the other part of it. But fortunately we know that entire part is 0.5. So if I can delete my mistake, which it won't, so I'll grab my eraser. We will subtract off the white space of 0.4834, and 0.5 minus 0.4834 is 0.0166. So the probability that we're less than 2.13 standard deviations below the mean is 0.0166. Let's do one more example. Let's find the probability that z is between negative 0.8 and 1.9. So we draw a picture. Negative 0.8 is off to the left, and 1.9 is off to the right. We want the area between them. Well, using our table, we can figure out each piece individually. So on the table, negative 0.8, that's the same as regular 0.8, 0.80, is 2881. 0.2881. And 1.9 on my table, 1.90 is 4713. 0.4713. We want both areas because they do both go into the center like we want, so we'll do 2881 plus the 4713 to get our total area on the calculator of 0.7594. I want to notice that as I did each of these, each one was slightly different. Sometimes we added the probabilities, sometimes we subtracted the probabilities, sometimes we did 0.5 plus the probability, sometimes we did 0.5 minus the probability. There's lots of ways that we can do to get to the answer depending on the question that's being asked. This is why I strongly encourage you always draw the picture of the normal curve, shade the area that you are interested in, and then figure out, do we add, do we subtract, do we need 0.5, do we not, and then work your way to the solution from there. I do want to touch on really quick, though, something that's called the empirical rule. It talks about how all normal distributions are kind of spread out. And so to set this up, we're going to have a big bell curve here. It's supposed to be symmetric. Work with me here. And mu is in the center. On the standard normal, it's 0, but this works for all normal distributions. is, first thing I want to know about the empirical rule is how much is within one standard deviation. One standard deviation to the left or one standard deviation to the right. Turns out there is about 68.27% within one standard deviation of the mean. So this blue area here is 0.6827. That's how much area is within one standard deviation of the mean. If we go out more to 2 standard deviations on each side, so this would include that center area, it turns out 95.45% of the data is 2 standard deviations from the mean. So that would be 0.9545 within 2 standard deviations from the mean. And we can go further. If we wanted to go 3 standard deviations, you pretty much have everybody. They say 99.73% of all the data is within 3 standard deviations of the mean. I would not expect to ever see a z-value greater than 3 covering all of this data. 3 standard deviations on each side, 0.9973. So if I ended up with something with a z-value of maybe 4.8, 4.8 standard deviations from the mean, that is way out there. Notice 3 standard deviations was 99%. 4.8 is going to be basically impossible. That would be odd. And that's one reason why, if you look at your table in the bottom right, we only go to 3.9. Because 3.9 is pretty far away from the mean. Turns out that you've got basically no area left after 3.9. So if you're ever having to go past the end of the table, just assume you've got the entire side. So in this case, if I wanted 4.0, we'll just assume 4.0 being off the chart is all of it. We're going to give it a 0.5 area. Because for all intensive purposes, it's going to be close enough. It's going to be within 1/100th of a percent of accuracy, and probably less than that. So that's the empirical rule. 68% in 1 standard deviation, 95% in 2, 99% is within 3 standard deviations of the mean. Let's do a more realistic example, though. Let's say the average computer in a study is used 2 hours per day with a standard deviation of 0.5 hours. We're going to answer several questions about this, but let's first identify the 2 hours per day. That's the average, so 2 is going to be our mu. 0.5, that's our standard deviation, or our sigma. So if we were to graph this just to begin with, mu is going to be 2, and the standard deviation is going to be 0.5. And the 0.5 determines how tall that curve is going to be. It's going to be very, very tall with a small standard deviation, short with a bigger standard deviation. We're going to find the probability a computer is used between 1.8 and 2.75 hours. Probability that our variable x is between 1.8 and 2.75. Now, the catch here is we don't know or have a table for every single mean and standard deviation. That would be exhaustive and a waste of time. So what we're going to do is we're going to normalize this, and we're going to change this to a z-value between two things. Remember that equation was z is equal to x minus mu divided by the standard deviation. This is a formula you want to have memorized. It's going to make life a lot quicker for you in the future. So first with the 1.8. 1.8 is the x value on the left side, minus mu, minus 2, I said 2 was our mean, divided by the standard deviation we said was 0.5. On my calculator in 2 steps, 1.8 minus 2 is negative 0.2, divided by 0.5 is negative 0.4. So we want the smallest z value to be negative 0.4. Same thing with the 275. We need a z value. So 2.75 is the x, minus mu, which is 2, divided by the standard deviation, which is 0.5. So 2.75 minus 2 is 0.75, divided by 0.5 is 1.5. So now, if I draw my standard normal at 0, the negative 0.4 is to the left, the 1.5 is to the right, and we want z to be the area in between. So let's go to our table to find the left and right side. First, the 0.4. And I'm going to clean up my table here because it's getting crowded. You probably don't want to write on your table. All right. 0.4 on the table. There was nothing after the 0.4, so it must be 0.40. So that area is 0.1554. 0.1554. The other side is 1.5. 1.5. Nothing after that is a 0, so 0.4332. 0.4332. Because we want both areas, we're going to add them together. 0.1554 plus 0.4332. A little help from our calculator, we got a 0.5886 probability. So the probability that this computer is used between 1.8 and 2.75 hours is about 58-59%. We got that value by first taking our data, which is x, and changing it to z, using that x minus mu divided by sigma, and then finding the appropriate areas that correspond in our tables. Let's try another one. Same information. Computers used an average of 2 hours, standard deviation of 0.5. What is the probability a computer is used more than 2.5 hours? So we're asking for is the probability that my computer, variable x, is more than, greater than 2.5. Of course, x is not going to be useful to us. We need to change 2.5 to a z. Z is equal to x minus mu divided by the standard deviation. Write it every problem until you have it memorized. This equation we're going to use a lot. You should know it very well. X is 2.5 minus mu, which is 2, over the standard deviation, which is 0.5. All that's up above off my screen, should be in your notes. 2.5 minus 2 is 0.5, divided by 0.5 is 1. So we want to know the probability that z is greater than 1. So we have our mean of 0, our z of 1, and we want to be greater. However, remember the table is going to give the area between 0 and 1. So let's find that. Greater than 1. 1.0, no decimal afterwards, so that's 0.3413. 0.3413. But we don't want that area, we want the area to the right of it, because we want to be greater than 1. Well, the entire half is 0.5, so we'll subtract out the white space of 0.3413. 0.5 minus 0.3413 is 0.1587. So there's almost a 16% probability that a random computer is used more than 2.5 hours. How about the probability there we go, a computer is used less than 2.25 hours. So we want the probability that our variable x is less than 2.25 hours. We're going to convert that to a z less than something so we can use our table. Z is x minus mu divided by standard deviation. So the x was 2.25 minus mu, which was 2, divided by the standard deviation, which is 0.5. 2.25 minus 2 is 0.25, divided by 0.5 is 0.5. So we want the standard deviation to be less than 0.5 steps above the mean. So we go to our table. 0.500 is 0.1915. Oh, didn't draw a picture. What is that? I don't know. We didn't draw a picture. So here's 0. 0.5 is positive, and we want to be less than 0.5. So that's the area to the left. So the 0.5 is 1915. So that area is 0.1915. But we also want the left side. We want all of it. So that area is 0.5. So my probability is 0.5 plus 0.1915, which is 0.6915, is the probability that a computer is used less than 2.25 hours. We can also work the table in reverse. Instead of finding a z-score that corresponds with, instead of finding an area that corresponds with the z-score, we can start with the area and work backwards to the information we want. Let's say, what if we want the 90th percentile? When we say 90th percentile, we want the value, we'll start with the z value, that has 90% of the area, or 0.9 of the area below it. That's what a percentile is. 90% of the area below it. We already know then that the left half has a combined area of 0.5, which means what's left for the right half? 0.4. adding some zeros, we are looking for an area of 0.4000 in the table. We know the area. We want the z-value of 0.4000. We're looking for that on the inside of the table. It's going to happen somewhere between here. We see 3997 and 4015. The 3997 is closer, so I'm going to go with that value as the winner. So when we get our combined points, that's 1.28. Our z-value is 1.28. So we used the chart backwards. Knowing the area, we found the area and what number went with it. But that's our z. It won't make any sense to say we're less than 1.28 standard deviations above the mean. What we want is we want the x value that has meaning in terms of the number of hours the computer is on. You recall the formula that x is equal to z sigma plus mu. It's the same formula solved for x, so we're going to work backwards. We want x. Z we just found out was 1.28. Sigma we know is 0.5 hours, plus the mean, which we know is 2 hours. So on my calculator, 1.28 times 0.5 plus 2, x is 2.64 hours. 2.64 hours marks the 90th percentile. That 90% of computers are used less than 2.64 hours. So we can use the table in reverse. One last example. We're going to find what is Q1. What is the first quartile of computers? Well, what does Q1 mean? Q1 means 25% of the data is below 1/4. That's where the 1 comes from in Q1. Which means we're really looking for the 25th percentile. And visually on a picture, 0 is the mean. We're looking for the point that's got 25% of the area below it. And we know it's to the left because we have to go to the left. The left has 50% in it. So if that left area is 0.25, we want the right area to also be 0.25, so they add up to 1/2. Sorry, so they add up to 1/2. So we're looking for 0.25 in the body of the table. So where is 0.25 in the body of the table? Looks like it happens right in the middle of these two values. So I'm going to come up right in the middle just because that one's in the middle. So I'm going to call that 0.6 from the left, and then I'm going to do 7.5 to get right in the middle of 7 and 8. So 0.675. What I want to notice for the z-value of 0.675 is we are to the left of 0, so that z-value has to be negative. Negative 0.675 to keep us to the left. Otherwise, we'd have more than 50% of the area. And we know our x formula is z sigma plus mu. Plugging in what we know, x is z negative 0.675 times sigma, which is 0.5, plus mu, which is 2, and negative 0.675 times 0.5 plus 2 gives us the Q1, where 25% of the computers are below first quartile of 1.6625 hours. If you made it a fraction, it would be 53/80ths of an hour. That's not really good. Maybe we'll say 1 hour, 39 minutes, 45 seconds. So this is the normal distribution. It's a bell-shaped curve. Many things in statistics and the studies that we'll do will follow this, and we'll talk about why when we get to the central limit theorem in Chapter 7. For now, what we want to get really good at is taking a problem like number 5, where we've got the mean and the standard deviation, standardize it by changing it to a z-value, x minus mu divided by sigma, and then use the table and the areas to calculate the area or probability that we're looking for. That is the normal distribution. We'll see you in class to continue working with it.